The first talk in this afternoon session after coffee is Dominic Vella from Oxford, and he's going to talk on floating with surface tension from Archimedes to Keller. Dominic.
Okay, thanks very much, Brian, and thank you again to the organisers, both for organising and for giving me the opportunity to talk. The one time that I met Joe was, as with many people, at Woods Hole, and I wanted to show the photo, the staff photo on the footsteps of Walsh Cottage, partly because it shows you that Joe was really an integral part of everything. He was right at the centre and at the front there, but also because there are a great number of people in this photo who are also in the room. So I think Andrew Fowler is somewhere here, Paul Della, myself, and then possibly a couple of others as well. And one of the things that was great about Woods Hole was the opportunity to talk to these great people, including George Veronis, Herb Keller, and Joe. And I think that's one of the things that's really unique about Woods Hole is the opportunity to have the chats on the porch of Walsh Cottage. And I wanted to start off by talking about one of Joe's papers, partly because I think that it must have, it's this paper that was mentioned earlier, this very short paper from 1998 on the surface tension force on a partly submerged body. And one of the reasons that I wanted to talk about it is because of the acknowledgements. Okay, so the acknowledgement suggests that maybe this was a result of a Walsh Cottage chat, because at the end, Joe says, "I'd like to thank George Veronis for asking the question that led to this work." So what is the question? Well, I think we all know a little bit about floating. We know about Archimedes' principle. And Archimedes, writing roughly 250 years BC, said that any object that's wholly or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid that's displaced by the object. And that's fine, every school child knows that, but it's sort of almost a corollary of this, that an object can only float if it's less dense than water. And it's quite easy to show that that's not true. I demonstrated that to my 5-year-old daughter when it was her homework a couple of weeks ago, because you can take a drawing pin and float it upside down on the surface of water, okay, and the drawing pin is made of metal, so it's clearly much denser than the water. Okay, so the question is, what's going on? This is actually a question that's been known or a problem, or apparent problem that's been known for a very long time. And actually the next step after Archimedes is Galileo, who, if you look in his Discourse of Floating Bodies, has a picture that looks very similar to the drawing pin that I just showed you. There's a rectangle which is meant to represent a small chip of ebony, okay, and ebony is more dense than water, okay, and he was in dispute with various other scientists of the time who were interested in the nature of density, or what makes an object float, okay, and their argument was, why does this ebony float if it's more dense than water? And so you sort of have to, so Galileo came up with, I think, Theorem 6, which is maybe written in slightly old-fashioned language, where he basically says that it's not just how much water is displaced by the object that matters, but there's this little rampart, he calls it, here, which is displacing some liquid. Now, today we'd call that the meniscus, but essentially what Galileo is saying is that you have to think about not just the volume of liquid displaced by this body, but also the sort of void that forms above it. And once you've taken into account that, then you go back to Archimedes' principle, more or less. Okay? So Galileo's picture is that if you think about the total amount of liquid that's displaced by the object and its meniscus, then you have a very simple Archimedes' principle, more or less. But we're more used to maybe thinking about surface tension as being a force per unit length, okay? So if you think about the force on an object from surface tension, it's very natural to say, oh yes, I've got a contact line and I've got some gamma that's pulling up tangential to the interface, okay? So how do we reconcile these two pictures? And that's where Joe comes in with his paper from 1998, and I've just taken a sentence from the abstract of that paper where he basically says that the vertical component of the force is equal to the volume, or the weight that's the weight of the liquid that's displaced by the meniscus. Okay, so that's Joe's theorem, if you like, and it's a very simple exercise in the divergence theorem, okay, because he essentially says, well, you know that the force from surface tension is the surface tension coefficient times the tangent to the interface crossed with the normal, tangent to the contact line crossed with the normal to the interface integrated over the contact line. Okay, and then if you dot that with the unit vector in the k direction, and then basically project onto, sorry, what am I doing? So this is a projection of the contact line onto the xy plane. Okay, then you can use the divergence theorem to get rid of the normal to the contact line and write it in terms of the curvature of the interface out here. And once you've got rid of the details of what's happening at the contact line and you know what's happening in terms of the curvature of the interface, then you can use the equilibrium of the interface, which is a Laplace-Young equation, basically equates the hydrostatic pressure in the liquid to the curvature pressure or the jump in the pressure due to the curvature of the interface and surface tension. So once you substitute this Laplace-Young equation into this expression up here, then you can see that you essentially have that the vertical force from surface tension is equal to the volume that's displaced in the meniscus outside, and that's Keller's theorem. So why is this important? Well, I think the reason I think it's particularly important is because in the sort of early 2000s, so after Joe's paper, there were a lot of interest in various insects that walk on the surface of water. And people were very interested in why or how do they do this. And they got, I think, a little bit distracted about the fact that these insects have very hairy legs. Okay, and the sort of the intuition that they had was, well, you know, surface tension is a force per unit length. So if I have a hairy leg, then I have a lot more contact line length, and I'm multiplying that by surface tension coefficient, and so that's going to give me more force. What happened? Nothing. Okay, good. So several people working on water striders and other insects at the surface of water sort of postulated that the reason that these insects have a very hairy leg is because it gives them much more force to support their weight at the interface. And once you understand Joe's theorem that the force from surface tension is just the weight of liquid that's displaced by the meniscus, you realize that that can't be correct. Okay, so you realize that if you look at a deflected leg, it's just basically the same as it would be if it didn't have hairs on it. Okay, there's a slight technicality about whether it's hydrophobic and how hydrophobic it is, but more or less the fact that it has hairs doesn't really matter. Okay, so that's something that I think people haven't really understood. And then the question is what's wrong with this intuition about having lots of contact line length? And the answer is that if you think about what the meniscus looks like between these very small hairs, it's not vertically upwards providing a vertical force. Instead, they're going to be roughly horizontal, and so you're not going to get very much vertical force from them at all. Okay, so that's Archimedes' principle and why it's useful, or it's an important thing to think about. Okay, as we saw earlier with the bouncing drops, it sort of gives you some intuition also for what's happening in more complicated situations. So I just wanted to show a movie of what we call the inverse Leidenfrost effect. Okay, the inverse Leidenfrost effect is what happens if you take a drop of water, which is going to be colored red here, and then you drop it onto a bath of liquid nitrogen. Okay, so that sounds like a very strange thing to do, but people are interested in doing it as a way of doing cryopreservation. Okay, so you want to make your cells freeze in a particular way, and the way you do that is basically by dropping them onto a bath of liquid nitrogen. So what happens in this situation? Water is more dense than liquid nitrogen, okay, about 20% more dense, and it initially floats at the surface and it's levitating. Okay, so there's a thin cushion of nitrogen vapor, and the pressure in that vapor is what's holding it up. But from a sort of modeling point of view, you can think of that as just being a non-wetting sphere. You don't need to worry about the details of what's happening in the thin layer. Okay, and then at some point something goes wrong. Okay, and what we've done sort of some more detailed modeling, but the sort of essential thing is that once the object is frozen, okay, so the water drop is getting cooled by liquid nitrogen, so it's freezing. Once it's frozen, it no longer has the sort of thermal deficit that allows it to levitate, and so it comes into contact with the liquid nitrogen and then it sinks because it's more dense and it's got a rough surface. Okay, so that's Joe's contribution to Archimedes' principle, but I think it's useful not only because it allows you to think about what happens with these insects, and I've forgotten to put an equation here, but I'll tell you that in a second. It's also useful as a way of sort of thinking about more complicated problems that people have thought about in the past. So one example of that is the meniscus on a very, very small cylinder. Okay, so what's meant to go in here is that there's a small parameter epsilon, that's the radius of the cylinder divided by the capillary length. Okay, and if that's very, very small, then you can sort of do a matched asymptotic expansion that takes account of the fact that the slope of the interface here is quite large and has to match onto something where gravity matters out here. Okay, but that's a reasonably detailed calculation. I just wanted to show you how Joe's generalization of Archimedes' principle allows you to do that calculation a bit more simply. And the idea is the following. The idea is basically you can say that if I'm far away from the cylinder, then I know that the deflections are going to be small, and I can linearize the Laplace-Young equation. Okay, and this is just a modified Bessel equation. So I know that the meniscus deflection zeta is just going to be some constant a times a Bessel function. Okay, now how am I going to calculate that a? Well, in a sort of conventional approach, what you do is you sort of match into this region where there are two curvatures, one sort of around and one in this direction. What we're going to say instead is that the mass or the weight of liquid that's displaced in this outer meniscus has to be balanced exactly by that surface tension force, which is just 2 pi gamma times r cos theta. Okay, and we know from Joe's generalization of Archimedes' principle that those two quantities have to be the same. And when you do that calculation, then what you find is that the final height of the meniscus compared to the capillary length LC, which is defined up here, is basically epsilon log epsilon. No, sorry, or epsilon log 1 over epsilon. It's the same thing. So this is the radius of the cylinder log the radius of the cylinder compared to the capillary length. Okay, so we're going to come back to think about why this is significant in just a second. But I wanted then to talk about a second paper of Joe's that's been very important. It's been particularly important in the literature on drop breakup. Okay, and the problem was is a paper by Joe and Mike Mixis in 1983. Okay, and what they studied was the retraction of a wedge of fluid, and they did this at high Reynolds number, and the retraction is really governed by or controlled by the surface tension, and they impose a far field angle. Now, Joe was motivated by the breakup of a wedge, but this is also sort of the problem of what happens when you touch a liquid surface. So if you start off with a liquid surface that's flat, and then you bring a plate up to it, then you know that at some point the plate is going to touch the surface and jump to form a meniscus. And so this calculation by Keller and Mixis is really the problem of what happens when a plate touches a liquid surface. Okay, the interface is going to spring up, but you have to kind of rotate their picture slightly so that you imagine having air above water. And Joe and Mike Mixis found these similarity solutions for the interface shape for different contact angles. Okay, so I don't think Joe and Mike sort of mentioned this in their paper, but it is sort of a motivator for a later paper by Christophe Clanet and David Keller, where they take a small cylinder. Okay, so here the radius is 200 microns. Okay, and they just touch the surface of a hexane bath, and what happens is that the liquid jumps up and it kind of gradually spreads. Okay. Now, Christophe and David were really interested in several different regimes of this problem. They changed the cylinder radius, they changed the viscosity. Okay, and the question that they tried to address is, well, how does the meniscus height change with time? Okay, so the Keller and Mixis analysis from the 83 paper is a high Reynolds number analysis, and it's only really relevant to large cylinders. Okay, and I'm being deliberately vague about what I mean by a large cylinder, because that's one of the things I want to come back to in a second. So Clanet and Keller gave a sort of scaling analysis, which essentially gives you the same scaling as what Joe had in his 83 paper. The basic idea is that surface tension is pulling up on the liquid here, okay, and then Newton's second law tells you that the mass or the momentum in the meniscus has to change at a rate determined by that force. Okay, and then if you assume that the contact angle of the liquid is fixed, then you find that the mass of the meniscus goes like h squared, and by the time you sort of shove this into here and then integrate it, you find that the height goes like the t to the 2/3, okay? So this is exactly what I think is commonly referred to as the Keller and Mixis scaling, okay? It's not the scaling analysis that's done in their paper, and their paper is more detailed because it also gives you the prefactor in principle as a function of the contact angle. I'm not sure if that's me or... Okay, so Clanet and Kerre did some experiments with very large cylinders, and you see very nicely this t to the 2/3 scaling, and then it saturates at some point because the meniscus reaches its final equilibrium height. Okay, so that seems to work very well, and you see essentially no dependence on the cylinder size, provided that the cylinder is large. Now, the next step is to do this for a smaller cylinder. Again, I'm being vague about what I mean by a small cylinder, but the basic idea is to do the same thing again, to say, okay, I've got a mass times, so I've got a momentum, and I'm looking at the rate of change of momentum and balancing that with the force from surface tension. And again here, geometry gives you that the mass of the meniscus goes like the density times the height cubed. And if you plug this in, then now you find that the height goes like t to the power of a half. Okay, so it looks like they've broken the t to the 2/3 Keller and Mixis scaling. And this is their experimental data, which seems to show a 1/4 power here. So that they plot t squared on the x-axis, and you apparently have 1/4 over here. I just tried that. I don't know. No, thank you. I'm not sure. Okay. So it looks like they've got something different, a diffusive growth, rather than the t to the 2/3 from Keller and Mixis. So I sort of hoodwinked you very slightly, and maybe people noticed and maybe they didn't. I said that the mass of the meniscus goes like the height of the meniscus cubed, okay? And that's sort of plausible if you have a very thin cylinder and a very large meniscus, okay? Because then you don't care about the radius of the cylinder. And that's really the important step in giving me the square root time scaling. If instead I have a fat cylinder, then I get the t to the 2/3 of Keller and Mixis. So that sounds fine. Why am I saying that I hoodwinked you? Well, you remember that earlier I told you that an application of Keller's theorem to the meniscus on a cylinder tells you that the final height goes like the radius times the log of the radius. Okay? So in the ratio of the meniscus height to the radius can be at most log of the radius. Okay? So the separation of scales that lets me get this scaling doesn't work unless log of r is very, very large. Okay? So the question is what happens, and you should expect that at early times you get the same scaling. This is what really happens in our numerics, and we see, so we basically do the potential flow problem with a constant contact angle that's equal to the equilibrium value that's measured by Clanet and Kerre, and our numerics roughly goes through the experimental points, okay? And the key thing is that I really want to say is that there's, in this Keller and Mixis scaling, there's also a horizontal length. You have a vertical length that goes like t to the 2/3. Because you're imposing a constant contact angle, you also have a horizontal length that's the same. Okay? And so what I mean by a large or small cylinder is really whether the radius is large or small compared to t to the 2/3. Okay? So it motivates introducing a ratio of these two length scales, and you can sort of generalize Joe's analysis to find the similarity, or the effective, it's a sort of family of similarity-like solutions that are parameterized by this parameter, the radius of the cylinder compared to t to the 2/3. For infinite cylinders, you get back the Keller and Mixis solution, and otherwise you get something slightly different. But we are able to look at the Clanet and Kerre experimental data and collapse it all onto a universal curve. So t goes in this direction. Initially, you start off with a big cylinder. The cylinder looks big compared to your meniscus, so it's basically planar. And then as it realizes that the meniscus should be curved in the other direction, then you get something slightly different. Okay, so in conclusion, I wanted to say that there are two ways of thinking about the vertical force from surface tension, and you should choose whichever is most convenient, provided that you're logically consistent and what the other one tells you isn't contradictory. And then secondly, you can sort of extend this classic Keller and Mix's similarity solution to a problem that does have an intrinsic length scale but gives us instead a family of similarity solutions. So with that, I'd like to thank you for your time.